I would like to start with saying thanks to the organizers of this wonderful meeting. I'm for the first time in Korea and I enjoy it very much. And well, I was going to speak about Schubert polynomials and pipe dreams. Well, Schubert polynomials, you probably heard about that. Well, or at least today you heard a lot about Schubert calculus, and this is a very closely related thing. And about pipe dreams, I'll tell you in 10 minutes. Well, here's the outline of my talk. First, I'll recall some basic definitions about flag varieties, Schubert varieties, Schubert calculus, and so on. And then I'll tell you what the Schubert polynomials are, and say something about their numerology, and about combinatorics related to Schubert polynomials, about pipe dream complexes, well, about some nice complexes. So, well, some of them give some nice some nice polyhedra, and well, I'll end up with some open questions. Okay, so let me start with the definitions. In the first 25 minutes of my talk, I will work with full flag varieties of type A. So I start with the group GLN. Well, let's say over C, but the base field doesn't matter much. And I take I fix a Borel subgroup. Well, as the simplest example, you can fix the subgroup of upper triangular matrices, and you consider the variety of full flags, namely of n. Where's the pointer? Okay, of n tuples of well, the origin inside a line, inside a plane, etc., etc., such that the dimension of vi is equal to I, and this is a homogeneous variety of G. And the stabilizer of a point is isomorphic to B, so the whole thing is just a homogeneous space G mod B. Okay, and people study this variety for a long time, and well, one of the important contributions was done by Borel in mid-50s in his thesis. He computed the cohomology ring of this variety. It turned out to be the isomorphic to the ring of polynomials in n variables, where n is the dimension of the ambient space, mod out by the ideal generated by all symmetric polynomials without constant term. Well, this is to say that you should take all elementary symmetric polynomials and generate the ideals by them, and mod out the whole polynomial ring, and what you get is a graded ring, which is isomorphic to the homology of G mod B. And you can even say what these mysterious x1, etc., xn are. Well, they have a very nice geometric meaning. If you have a flag variety, you have n tautological vector bundles over it, namely over each point you have an n tuple of spaces, well, represented by the corresponding to this point of the flag variety, right? So you have these vector bundles, and you can mod out each of them by the previous one. So you get an n tuple of line bundles, and for each of them you can take their first Chern classes with a negative sign for some reason, and these Chern classes correspond exactly to those x1, etc., xn. Okay, so this is a classical result of Borel, which describes the cohomology ring of a full flag variety, well, in, let's say, multiplicative terms. And let's now describe it as an additive group without the multiplication structure. It turns out that this ring also has some very natural basis as an abelian group. For this, you need to take Schubert varieties. Well, these are the following guys. Well, let's take the Brouillard decomposition of GLN. Namely, you can represent each matrix as as a product of an lower triangular matrix from the group B minus, some permutation matrix of zeros and ones, and an upper triangular matrix. And this is the Brouillard decomposition of GLN, and this gives you the Schubert decomposition of your full flag variety. So your full flag variety is represented as disjoint union of such B minus WB mod B. And these are, each of those is isomorphic to an affine space. And so their geometry is not very interesting, but things become interesting once you take the closure of each of them. And those guys identified by XW, and they are called Schubert varieties. And they have many nice properties. They were studied for the last 150 years, something like that, because of the purposes of enumerative geometry. And one important property of Schubert varieties is that their classes span the cohomology ring of the full flag variety. Okay, so we have two presentations. One is multiplicative in terms of x1, xn, which are negative Chern classes of line bound also on the full flag variety, and the other is additive, and this is related to Schubert varieties. So you would like to relate one to the other. So we would like to find nice representatives of these guys of the classes of XW inside the polynomial ring. And the answer was obtained in late 70s or early 80s by Lascaux and Schützenberger, and before much of this work was done by Bernstein, Gelfand and Gelfand. And they described Schubert polynomials, some nice polynomials which represent the classes of those XWs. They correspond to certain nice lifts of those classes into the polynomial ring. And they have many properties. These are polynomials in fact an n-1 variable with non-negative integer coefficients, and their combinatorial description, which proves the positivity of their coefficients, was obtained by Sergei Fomin and Anatol Kirillov, and independently by Sarah Billy and Nathan Bergeron in early 90s. So I pass to this description now. Okay, so now some combinatorial game begins. So let me fix a permutation in n letters, and having such a permutation, I would like to construct pipe dreams corresponding to this permutation. These are pictures of the following type. They are formed by elements of two types, of crosses and things I call elbow joints. And here you have a couple of strands entering the picture from the left and leaving it from the top. So here I have permutations. Here I have pipe dreams corresponding to the permutation 1, 4, 3, 2, and you see that on each of those pictures, the strand starting from 1 goes to 1, the strand starting from 2 goes to 4, 3 goes to 3, and 4 goes to 2, right? And one more technical requirement is that I allow any two strands to cross at most once. They're not allowed to cross each other twice. So here, and having, as you see from this example, for a given permutation, you can have more than one picture representing it. This picture is called pipe dream, because it resembles some pictures from a certain video game, which was popular in early 90s. A game was like Tetris, and you were supposed to construct a pipeline from such elements which have fallen randomly. Well, so I see that some of you remember that game. Okay, so here, well, this is exactly the same game. I have a permutation, and I draw all possible pictures of this type. I get a bunch of such pictures corresponding to a permutation. And then to each of such pictures, I can put into correspondence a monomial in n-1 variable. Namely, to get a monomial, I count the number of pluses of crosses in each row, and I let the number of crosses in the first row be equal to d1, and the second row to d2, etc. And then, having such a tuple of integers, I consider the monomial x1 to the power d1, x2 to d2, etc., xn-1 to dn-1, and you see that xn has always multiplicity 0, because I'm not allowed to have any crosses in the last line, because my pipeline will not be closed. The water will just go out, and I don't want this to happen. So for each of these pictures, I have a monomial. So for instance, for this guy, for the third one, I have 2 crosses in the first row, no crosses in the second row, and 1 cross in the third row. So my monomial is x1 squared times x3. And I get the same thing for all pipe dreams. Okay, now I started with a permutation. It's not true. Well, you can get the same monomial for different pictures.
Oh, you can.
You can, yeah, right. Yeah, thanks for this question. It's just a coincidence in this case that I got distinct monomials. But of course, different pictures can give the same monomial. Okay. The coefficients are positive or equal to 0, but they can be more than 1, right? So to get the Schubert polynomial, I just need to sum up all those guys corresponding to all possible pipe dreams, and what I get is exactly the Schubert polynomial corresponding to the permutation W. Okay, and this is a theorem proved by Sergei Fomin and Anatol Kirillov in 1994. Well, so here, the Schubert polynomial corresponding to a permutation W is equal to the sum of x to the power d of p over all reduced pipe dreams p corresponding to the permutation W. The word reduced means that no 2 strands in my pipe dreams cross more than once. Okay, so for example, in the previous case, I get this this polynomial. So this polynomial corresponds to the class of Schubert variety corresponding to 1, 4, 3, 2 in the cohomology ring of GL4, right? Okay, and what happens if you plug all ones instead of x's? Then just you get the number of those pipe dreams. So an obvious corollary is that the number of pipe dreams corresponding to W is equal to the value of my Schubert polynomial at the point 1.
Should they reduce?
Reduced pipe dreams. Yeah. The word reduced is missing. Yeah, thank you. Okay. And since I'm here and the conference is called torus actions, then I need to explain what's the relation of this story with torus actions. Well, there is such a relation. Namely, as you know, full flag variety is not toric. So it seems to have nothing to do with this conference. But still, you can degenerate it in many ways to obtain a toric variety. And one of the degenerations was described by Gonchoel and Lakshmibai. And you degenerate it and you get a toric variety. But this toric variety is not very good. In particular, it's not smooth. But still, this variety is, it's single, but it is still irreducible. And, if you have a toric variety embedded into projective space, it corresponds to some polytope. And this is the famous Gelfand-Zetlin polytope, and I think that Valentina will speak tomorrow about this topic, about Gelfand-Zetlin polytopes, about pipe dreams. So you'll hear the continuation of the story tomorrow. And my question now is that inside this flag variety, I have a bunch of Schubert varieties. And what happens to them once I degenerate the full flag variety? Well, the problem is that what I get, it may be reducible. It's, of course, it will be it will be also singular, but well, it's even worse. It's reducible, and its irreducible components are indexed by the pipe dreams corresponding to this permutation W. So the pipe dreams index the irreducible components of the toric degeneration of my Schubert variety. Okay, and well, this is one of the explanations why I will be interested in this number, in the number of pipe dreams corresponding to permutation W. Well, this number somehow measures how singular my Schubert variety is. Well, this I put very vaguely. Well, I can give some more precise meaning to these words, but let me just stop now. I just want you to believe me that the bigger this number is, the worse Schubert variety you have. The more singular it is. Okay. Yep.
A minute ago you said the same monomial comes from a different pipe dreams.
Same monomial can come from different pipe dreams. Yeah.
And then the coefficient has a geometry meaning, I suppose.
Think so, but well. I cannot answer this question now. Maybe let me think and answer later. Try to, at least. Okay, so I'm now. Well, the thing is that you specialize these pipe dreams in this x1, etc., xn, and this is kind of not, well, maybe not that natural. Okay, so I was just curious. I started to look at the number of pipe dreams for various permutations, and I tried to figure out what is the maximal number of pipe dreams corresponding to permutations in a given symmetric group. Okay, so I took the group S3, and in S3, well, there was only one permutation with 2 pipe dreams. All the others had only 1 pipe dream. And this permutation was 1, 3, 2. Okay, then I passed to S4, and then this was the permutation we saw several slides ago, and this was 1, 4, 3, 2, and the number of pipe dreams was equal to 5. Well, when I went further and well, considered as 5, and then the number of pipe dreams was equal to, for those 2 permutations, was equal to 14. So I think now you can guess what the next number will be. 2, 5, 14. Well, these are Catalan numbers, right? Right. Wrong. Because for S6, you have a permutation with not with 42 pipe dreams, but with 84. So the answer you get is twice the expected answer. And for n equals 7, things are even worse. This is 5 times the Catalan number. It's 660, and the Catalan number is 132. Okay, but well, those permutations, they all satisfy certain pattern. So, yep.
Did you put that sequence into the online sequence?
Of course I did. Of course I did. Well, I didn't yet put it as a new sequence, but but it's not listed. I don't know what sequence is it, but well, my first guess that it is always divisible by the corresponding Catalan number, and this turned out to be false for n equals to 9. Well, as it was shown by some undergraduate student of mine. Okay, so here I see that all my permutations satisfy a certain pattern. Well, you see that you can split this permutation into blocks like 1, 3, 2, 7, 6, 5, 4. Well, in each of those blocks, you make a flip, right? So let me give a definition that I call W a Richardson permutation if for a certain partition of the number n, this permutation has the following form. Each part of the partitions of my partition is flipped. So 1 to k1 goes to k1, k minus 1, etc. 1. Then the next block from k1 plus 1 until k1 plus 2 is also flipped, and well, same with the third block and so on. Okay, and I started wondering how to count the number of pipe dreams of those permutations. Well, it turned out to be possible. Well, the first theorem I found in literature was proved by Alex Wu in 2004, that if you take the permutation of the following type, that if you map 1 to 1 and flip the remaining part, what you get is exactly the Catalan number. And then well, the Catalan numbers have many interpretations. One of the interpretations is that they count sub diagrams inside a staircase Young diagram. Well, or this is also known as dig paths. And it turned out that this theorem is generalized nicely to this permutation W naught Km, which is the following: 1 to 1, 2 to 2, K to K, and a flip on the remaining part. So a theorem which was found in by Fomin and Kirillov is that this number of pipe dreams is equal to the number of plane partitions of height k, of Dieck plane partitions of type k, namely sub-diagrams of such a prism. So for k equal to 1, you have a prism of height 1. So you just get sub-diagrams of this yellow guy. And well, in the general case, you have three-dimensional sub-diagrams of this three-dimensional Young diagram. And this number has also a determinantal. There is a determinantal formula for that. And well, here's our big and scary formula for the Schubert polynomial of such a permutation. Well, it resembles slightly the Jacobi-Trudi formula, but there are some denominators with some ugly powers, and I don't want you to look at this now. So I just propose you to compute the value of these functions at 1, and so fortunately all the denominators vanish because, well, you divide by 1, and you get the following nice expression for the number of pipe dreams corresponding to this permutation. This is the determinant of such a Catalan-Hankel matrix. Namely, you take the sequence of Catalan numbers and you put the first k numbers starting with m in the first row. Then you shift by 1 and start from m plus 1 and do the same with the second row, and so on and so on. And well, you get the square matrix, compute its determinant, and it counts pipe dreams for such a permutation. Okay, and well, in the remaining 5 minutes, well, I pass to polyhedral combinatorics related with those guys, with pipe dreams. Namely, in 2004, there was a paper by Knudsen and Miller where they defined pipe dream complexes. Namely, to each permutation, you can associate a CW complex PD of W. its zero-dimensional cells correspond to pipe dreams, to reduced pipe dreams for W. And its higher dimensional cells correspond to non-reduced pipe dreams. I don't tell you what they are now, but still. Okay, and they proved that this complex is always homeomorphic to a ball, or in some cases to a sphere, in some kind of exceptional, some stupid exceptional cases. And let me give you one example with our favorite permutation 1, 4, 3, 2. There are 5 of those permutations, and I organize them as a pentagon. And if I consider non-reduced permutations, I get the blue guys corresponding to edges of this pentagon, and the green guy corresponding to the two-dimensional face of this pentagon. Well, in fact, all those 11 pipe dreams correspond to, are all pipe dreams reduced or not corresponding to 1, 4, 3, 2. Okay, so in this case, I get a pentagon. And what happens for the other Richardson permutations? Well, one theorem is as follows: that probably it's folklore. I found it by myself, but later I read it somehow between the lines in some paper by Vincent Pilot, and it's the result is that for permutation W naught 1n, namely 1 to 1, and flip on the remaining part of your set, your complex is the Stashev associahedron. So the vertices of this complex correspond to triangulations of an n plus 3 gon. So their number is equal to the Catalan number, and faces of upper dimensions correspond to dissections, to partial triangulations of this n gon. So in for instance, for n equal to 3, you get such a nice polytope with 14 vertices in 3-dimensional space. It has 14 vertices and 9 edges. Some of them are pentagons, some are squares. Well, okay. So that's one of the results, and I looked at some other Richardson permutations. So in this case, in the first case I have an associahedron. Then a non-interesting case is that if you take a transposition, which is also a Richardson permutation, you get an n plus 1 dimensional simplex. And if you take a 3-cycle like this, what you get is the dual cyclic polytope. What is the cyclic polytope? To do this, to define a cyclic polytope, you need to take, it depends on 2 parameters, n and d. And you take a Veronese curve of degree d in Rd. Well, the image of curve parameterized by t squared, etc., t to the power d, and then you take n points of general position on this curve. Their convex hull is the cyclic polytope nd. So this guy, which I get in this case, is dual to the cyclic polytope 2n plus 3 2n. And for arbitrary Richardson permutation, I don't know. I even don't know if this is a polytope or not. Well, once you have a complex, it takes certain effort to prove that it is actually a polytope. I don't know how to do that. Okay, but you can also generalize this for other types for other semisimple groups. And you can take a semisimple group. You can take it to Weyl group, and the analog of the full flip is the longest element in your Weyl group, denoted by W naught. And you can take various parabolic subgroups inside G, And for those parabolic subgroups, you can take their Levy decompositions into semi-direct product of semisimple and unipotent part. And you can also consider the longest elements for W in the Weyl group of this Levy part. And those are exactly your Richardson elements. Those partial flips of which I had in my symmetric group. And well, I can also define my pipe dream complex, which is in this case called subword complex. But to do this, I'll need to fix the reduced decomposition of my longest element in W naught inside W. Well, maybe Valentino will speak about this issue tomorrow or not. About fixing the decomposition of the longest elements. Oh, okay. So this I'll leave as a teaser for tomorrow. And well, in this case, you also can get subword complexes, and you get nice things in other cases, namely for Cn, well, where you had isosahedra in the type A, you get cyclohedra in type C. Those guys, well, the vertices of those guys correspond to symmetric triangulations of and gone with the even number of vertices. Okay, so in such a way you also can get all generalized isosahedra by Bernstein and Zelevinsky. Okay, so but still you have a bunch of questions. One of the questions is, well, the first question is whether what you get, the complex you get, is always a polytope. Or at least if whether this is true when your permutation is Richardson. And well, we see some nice polytopes as representatives of this family. What's the combinatorial meaning of this family? And well, one possible answer, which might be true, but I don't even dare calling it a conjecture, but just possible answer, that is that Buchstaber considered a family of two truncated cubes. Well, you can take cubes and remove their faces of codimension 2. And you get, well, in such a way you can get isosahedra, cyclohedra, and a lot of interesting stuff. A guess is that maybe our polytopes, well, our complexes can be obtained as two truncated cubes. Well, but I don't know how to prove that. Okay, I think that's all. I'll stop there.